Hello friends, welcome you all to the 42nd lecture on function analysis and its applications. In this lecture, we will discuss the further theorems on conjugate space H star. This is the content of today's lecture, further theorems on conjugate space H star. Theorem: the mapping psi such that H to H star defined by psi y is equal to Fy, where Fyx equal to inner product of xy for all x belonging to H. Here y is fixed in H, is one-to-one, onto, additive but not linear, and an isometry. Proof: first, psi is one-to-one, let y1, y2 belonging to H, then psi y1 equal to f of y1 and psi y2 is equal to f y2. We have psi y1 is equal to psi y2, that is f y1 equal to f y2. Okay. So this can be written as Fy1 of x equal to Fy2 of x for all x belonging to H. And as per the definition of Fyx as inner product of x and y, we can write Fy1x as inner product of xy1 equal to Fy2x as inner product of xy2. So by property of inner product, this can be written as inner product of x and y1 minus y2 is equal to 0. Taking x is equal to y1 minus y2. Okay. Or also we can write here inner product of x and y1 minus y2 is equal to 0. For arbitrary x belonging to H, it means y1 minus y2 is equal to 0, that is y1 is equal to y2. So taking x is equal to y1 minus y2. Okay. So because here x is arbitrary, so we can write x is equal to y1 minus y2. So inner product of y1 minus y2, that is norm of y1 minus y2 square is equal to 0. And we know that if norm x is equal to 0, if and only if x is equal to 0. So using this property, we have y1 minus y2 is equal to 0. This implies that y1 is equal to y2. Hence, psi y1 is equal to psi y2. This implies that y1 is equal to y2. Hence, psi is 1 to 1. Second, psi is onto. Let f be an arbitrary functional in H star. Then by rigid representation theorem, there exists a unique vector y belonging to H such that fx is equal to inner product of xy. Then by definition of fy, we have f is equal to fy, that is psi of y is equal to Fy, that is f. Thus, psi is mapping of H onto H star. Okay. So second, also proof. Third, psi is additive. If y1, y2 belonging to H, then psi of y1 plus y2. Okay. As per the definition of psi y, we can write psi of y1 plus y2 is equal to Fy1 plus y2. Now for every x belonging to H, we have Fy1 plus y2 x equal to inner product of x and y1 plus y2 by the definition of Fy. here. Okay. So by property of inner product, this can be written as inner product of x y1 plus inner product of x y2. Again, by the definition of Fy, this can be written as f y1 of x plus this f y2 of x. That is f y1 plus f y2 of x. This can be written as this. Hence, f y1 plus y2 is equal to f y1 plus f y2. That is, this one as psi of y1 plus y2, and this is psi of y1 plus this psi of y2. That is, psi of y1 plus y2 is equal to psi y1 plus psi y2. That is, the mapping psi is additive. Psi is not linear. Let y belonging to h and alpha be scalar, then psi alpha y can be written as f alpha y, okay, as per the definition of psi in terms of fy. Now for every x belonging to h, we have f alpha y x. As per the definition of fy, we can write this one as inner product of x and alpha y. As per the linearity property of inner product, this is outside the alpha bar. Okay. So as per the property of inner product of x and alpha y can be written as alpha bar into inner product of x y. Again, we apply the definition of fy. This can be written as alpha bar fy x, or this is alpha bar fy of x. Thus, we have f alpha y equal to alpha bar fy. Okay. So this is not linear. If here alpha fy, that is linear, but here alpha bar, so this is not linear. Okay. Hence the mapping psi is not linear mapping. Such mapping is called conjugate linear mapping. Fifth, psi is an isometry. Let y1, y2 belonging to h, then norm of psi of y1 minus y2 can be written as norm of psi y1 minus psi y2. We can write this one. Here if alpha is equal to 1, so f1y is equal to 1 into fy. Okay. So psi y is equal to fy. So we can write if alpha is equal to 1, that is linear. Okay. So psi y1 minus y2 can be written as psi of y1 minus psi of y2. That is norm of fy1 minus f of y2. And this one can be written as norm f of y1 plus minus 1 f of y2 using equation 2. Okay. This we can write this is f of y1 plus f of minus y2. Okay. And again using the property this, we can write this one as norm of f y1 minus y2. Okay. So f of y1 minus y2 equal to norm of f y1 minus y2 equal to norm of y1 minus y2. Thus psi is an isometry. Next theorem. If H is a Hilbert space, then H star is also a Hilbert space with respect to the inner product defined by inner product of fx and fy equal to inner product of y and x. Since a Hilbert space H is a nonlinear space, therefore H star is Banach space with suitable definition of addition and scalar multiplication in H star and norm of a functional in H star. Now, in order to prove that H star is Hilbert space with respect to the inner product defined by inner product of fx and fy equal to inner product of y and x, we are to show that the all property of inner product for fx, that is inner product of alpha fx plus beta fy and fz is equal to alpha into inner product of fx and fz plus beta into inner product of fy and fz. Second, conjugate complex of the inner product of fx and fy equal to inner product of fy and fx. And third, inner product of fx and fx greater or equal to 0 and inner product of fx is equal to 0 if and only if fx is equal to 0. We shall prove these one by one. In above theorem, first we have shown that f alpha y is equal to alpha bar fy. Therefore, alpha fy equal to f alpha bar y. Now, inner product of alpha fx plus beta fy and fz equal to inner product of f alpha bar x plus f beta bar y and fz. As per this definition, we can write this. Okay. So, here defined inner product of fx fy is equal to inner product of y and x. So, using this definition, we can write this inner product as inner product of z and alpha bar x plus beta bar y. Okay, by the definition of inner product in H star. This equal to inner product of the z alpha bar x plus inner product of z beta bar y by the property of inner product. And again, using the conjugate linearity of the inner product is, this is the bar of alpha bar outside the inner product, that is we can write this is conjugate complex of alpha bar zx plus conjugate complex of beta bar into inner product of zy. Okay. So, alpha double bar, that is alpha, and beta double bar, that is beta. So, this can be written as alpha into inner product of zx plus beta into inner product of zy. Again, by the definition of inner product in H star, that is this definition, inner product of yx can be written as inner product of fx and fy. So, this can be written as alpha into inner product of fx and fz plus beta into inner product of fy and fz. So, first is proved here. Second, since inner product of fx and fy is equal to inner product of yx, therefore, inner product of the conjugate complex of fx and fy, conjugate complex of the inner product of yx, okay, taking the conjugate complex of both sides of this, we have this one, and by the property of inner product, this can be written as inner product of xy. Okay. Again, by the definition of the inner product of H star, This can be written as inner product of Fy, and that is second property also proved. Third, inner product of Fx. Okay, so by the definition of the inner product in H star, this can be written as inner product of x and x. And we know that inner product of xx is equal to norm x square. Okay, so by theorem 1, norm x is equal to norm fx. Okay, so norm x square can be written as norm fx square. We know that the norm of f here, f is equal to fx. Okay, defined. And also we have already proved norm of f is equal to norm of x. Okay, so norm of f, this implies that norm of fx equal to norm of x. So this can be written as norm of fx square. So that inner product of fx greater or equal to 0, that is non-negative. And norm fx is equal to 0 if and only if fx is equal to 0. Okay, so third property also proved. This completes the proof of the theorem. Third, if x and y are two vectors in a Hilbert space H, then modulus of the inner product of xy equal to norm x into norm y, if and only if x and y are linearly dependent. Proof first part, that is if part. If x and y are linearly dependent, then modulus of the inner product of xy equal to norm x into norm y. If x and y are linearly dependent, there exists a scalar alpha belonging to C, that is complex numbers, such that y equal to alpha x. Because x and y are linearly dependent, so we can write y is equal to alpha x. The inner product becomes as inner product of xy equal to inner product of x and alpha x, putting the value of y as alpha x. So this can be written as alpha bar inner product of xx. This is alpha bar. Inner product of xy is equal to inner product of x alpha x, and by the property of inner product, this can be written as alpha bar into inner product of xx equal to alpha bar into norm of x square. Taking the modulus we have, this can be written as modulus of the inner product of xy equal to modulus of the alpha into norm x square. This is equation 3. Now the norm of y, here y is equal to alpha x, then norm of y is equal to norm of alpha x equal to mod alpha into norm x. Thus norm x into norm y equal to norm x, and putting the value of norm y as mod alpha into norm x, that is mod alpha into norm x square. Equation 4. So from 3 and 4, we see that modulus of the inner product of xy equal to norm of x into norm of y. Second part, that is only if part. If modulus of the inner product of xy equal to norm x into norm y, then x and y are linearly dependent. From the Cauchy-Schwarz inequality in Hilbert space, we have modulus of the inner product of xy less or equal to norm x into norm y, with equality hold if and only if x and y are linearly dependent. If modulus of the inner product of x and y equal to norm x into norm y, the equality in Cauchy-Schwarz implies that x and y are linearly dependent. Thus, there exists a scalar alpha belonging to C such that y is equal to alpha x. Okay? Because here modulus of the inner product of x, y. So, putting y is equal to alpha x, that is mod alpha into norm x square, and from here also x and y alpha x, that is norm of y mod alpha norm x, that is mod alpha into norm x square. Okay. So, this equality holds if we have y is equal to alpha x. That is, equality holds, then it should be here y is equal to alpha x, that is x and y are linearly dependent. In this lecture, we have discussed the further theorems on conjugate space H star. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresi. Second, function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.